Hey, what's up, everybody? We are back studying data structures and algorithms. We are maybe a little over halfway done with our first unit, which is about arrays, and we've been using arrays lately to make lists. We were making a list that could hold integers, and I just wanted to go over the documentation right quick. I love this feature of BlueJ that I can switch right here from documentation back to source code. And we've added a lot of methods, right? We can add to the back, add to a specific place. We can remove from the back, remove from index. Wouldn't it be easy for us to add a remove from front that would just call remove from index and supply this 0 and return what it returns? That's kind of an important part of programming, is reusing your methods that you've already made. So that's going to be a nice exercise for you to do. I want you to try that. I want you to write a method called remove from front that uses our remove from index method so you don't redo the work. The other thing I want to do this video is I want to talk about the big O of these different methods that we've added to our list. So at this moment, what I want you to do is two things for me. I want you to pause the video. I want you to write a remove from front method that returns what's at the front and removes it. Then what I want you to do is take some time trying to decide what is the big O of each of these different methods on best case, worst case, and average. Don't worry about whether you get them right or wrong, and you can think about it a little bit or just go with how you feel. I want you to build that intuition. We'll discuss in detail when we get back. So pause it now. All right, let's see how we did. I'm going to switch this over to source code, and we're going to write the remove from front. Okay, so I'm going to put that. I got remove from index. Let's see. Remove from back. My methods are a little out of order here, but that's okay. So I'm going to put it here. Public. Actually, no. I will put it after remove from back. Remove from front. All right, so what I'm going to do is I'm going to return remove from index 0. Now I'll just add some documentation here. Removes and returns the first entry in this list. It does not have a parameter, right? But we do return something, so we should use the @return. And we'll say the int removed from the front of the list. Here's a question. Could this method throw an error? Could it throw an index out of bounds exception? Well, it sure can, because if we were to look at the remove from index, if we try and give it an index of 0 and there's nothing in the array at all, then we are going to throw an index out of bounds exception right here. And I'm not really sure that's something that we would want to do. We would probably prefer to throw something like an illegal state exception, because it's not going to make a lot of sense to our users for us to say, hey, you can't do this because your index is bad, when they didn't give us an index. Likewise, we didn't discuss it at the time, but the remove from back can throw an exception for the very same reason, because when we remove from back, if we don't have any size, we could cause a problem. So I'm going to go ahead and add that to both of these methods now. All right, now we're ready to talk big O. And we're going to label each one of these methods with their big O runtime so that we can have that in our documentation so our users know what to expect. Let's go up and start with add. Well, right off the get-go, we start with the most confusing big O there is. Let's just get it out of the way. All right, so what I want you to think about is what happens, how much steps are required when we don't have to expand the array. Let's take a look. So I'm going to go ahead and just take a look at what this might look like pictorially. So I'm just going to draw a quick little array here. And let's assume that we have some items in there, like say a 7, and then a 1, and then a 3. And what we're going to be adding, we're going to call add, and we have plenty of room. See all this room in our array? And I want to add the number 5. Well, in order to do that, I simply have the code that says array bracket size equals 5. And accessing one specific location of an array is pretty much understood to be O1. It's really just one statement of code here, right? And we have instant access to any place in the array. That's one of the nice things about arrays, is that I don't have, in order to get to this position here, I don't have to start here and then move over. There's a lot we could look into about memory and how memory works to understand why that is. We're just going to go with this rule that accessing specific locations in an array is O1 time. So we're going to say that when we don't have to expand, it's O1. But what about when we have to expand? How many steps does that take? Well, after we've got this all filled out, and what did I say? I was going to put a 5 there. Let's say I will put a 5 and then a 12 and then maybe another 3 and then an 8. Ooh, that's a terrible 8. And a -2. All right, so now what has to happen? Well, what has to happen is I have to go through. I have to create this array, a temporary array, right? And all these things are blank when we start, right? So I got to go. I mean, if I really want to show this, I've got to get rid of all of these things, okay? They're all blank. Now, in truth, this array is double in size, right? So this whole thing here is actually twice as big. And I don't even have room, right? So we talked way back at the beginning of this course that when you create an array, we have to put some default values. So initially, this whole array, one by one, the computer has to go in and fill these with something, and they're all going to get filled with zeros. So if we have in items in this array, just creating the temporary array, when we expand, just creating that, before I even start copying things over, that right there is going to take twice as many steps as there are spaces in the array I'm about to expand. Then I got to loop through. I got to loop through each one of these, and I got to copy them over one at a time. One at a time. So that sounds pretty slow, right? Because we had to do 2 in steps just to fill in that array. Then we got to loop through each and every single spot in this array. I got to go here. I had to copy it, right? I had to go here, copy, copy, copy. How many things was I copying? In things. So there's another in steps after the 2 in. But I have 2 pieces of good news. First of all, remember, we don't have to worry about this being something like 3 in. because for the definition of ON, and go back to our introductory lesson on ON if you're not sure, tells us that we can just kind of disregard that 3 in front of the N. So this expansion, even though it has to loop through an array that's twice as big as N, the number of data points, and it has to loop through all the N data points again, we still just call that ON. Okay? Well, we have a problem. We have a best case and a worst case. Best case for O1, worst case for ON. But what is it on average? You know, on average, it's much closer to O1, right? Because you're not going to expand very often. At the beginning, we expand kind of often. We start with the size of 5, but you know, if you start with the size of 50, you're not going to expand that often. And we can actually add another constructor that allows the initial capacity to be set by the user. So if they know they're going to have to be storing quite a bit of items, they can start with a size that big. But what we're going to say is that this is functionally O1. And I don't want to go into too much detail about that. You can read about that online. You can read about it, the documentation for ArrayList on the Java docs. But basically, what we're saying is that it's going to behave to you as if it's O1 to add. Okay, and we're just going to leave it at that. So that one's kind of weird. The rest, hopefully, will not be requiring near so much debate. All right, so we're going to say that this is functionally O1, right? That's as fast as you can get. All right, what about this one? We're going to add an index. Okay, so let's go back to our picture here, okay? And let me just clean this up a little bit. Kind of went crazy with all my little drawings, didn't I? Let's just get rid of that. And let's say we've already discussed that we're not really going to consider the rare moment when we expand. So here's a situation where I can add without expanding. I want to add the number 9, okay? And I want to add it to a specific index. So I want to add it right here, okay? This is where I'm going to add the number 9. Well, what do I have to do? Well, the first thing I've got to do is I've got to, even though I'm not having to expand, I've got to go through every one of these things after it and move it back. Okay, so as you can see, even when we don't have to expand, we definitely have to move a lot of items back. So let's talk about the worst case scenario. Well, worst case scenario would be you're adding to index 0. So if you add to index 0 and you have n things in your list, you have to move all n of those things. So the worst case scenario is definitely O n. We saw that when we tried to add somewhere like right here, when we tried to add something here, we had to move almost all of the n. So I'm going to say that the best case scenario would be if your index that you're adding is right here at the end, and you're just going to plop something right there at the end. So at best, we're O1, right? So then what would we be on average? Well, on average, it seems like we're going to have to move. You know, if our average case, sometimes we have to move a little more than half, sometimes a little less, sometimes all of them, sometimes none of them. But on average, we're going to have to shift over about half of our items in our list. So if you have n items, you might think that the average case would be n over 2, right? Because we had to move half of them. But just like how we didn't have the 3 times n or anything like that, well, it works both ways. We don't have to worry about saying O of 3n, but we also don't get to say O of n over 2. We just have to say O(n). So yeah, that can be kind of slow if we have a lot of items that have to move that many. So definitely adding to the front is quite slow. Adding to the end was fast, right? Adding in general, just O1. That's one step. So if I have 10 billion numbers in this list, I can add to the end of it just like that. But if I have to add to the middle of it, it might take a little while. All right, so what I'm going to do is we're going to go back to this added index, and let's just go ahead and add that. that this turned out to be O in runtime. Or O in, I don't like that. Let's say O in complexity. All right, so let's take a look at the get method. Well, let's see here. We check to see if our index is okay. That's just a couple of steps. And then we directly access a specific place in the array. And you remember what we said about accessing a specific place in the array? We can go anywhere we want, just like that. This is O1. So O1 complexity or O1 speed, however you want to say that. All right, removing from the back. So when we remove from the back, that's a little different situation than when we remove from the front or from an index. So let's go ahead and quickly look at removing from the back. So when we remove from the back, we simply take this item here, we send it back to the person that called it, and we decrease size. So earlier size was pointing here, and now it was here. So that might take a few steps, but if you think about it, it doesn't depend on the number of elements in the array. If I have 1 million elements in my array, I can immediately access the last one, grab a copy of it, shift size down one to delete it from my list, and send it back to the user. So the number of steps that it takes does not depend on how many items are in the array. So I hope you can guess it. This is O1. And you can look at the code. You can see that there's no looping or anything like that, no going through the end values. So this is just O1. Well, but what about removing? Let's come back to remove from front. Let's go to remove from index. Well, if we remove from index, you'll notice that we have to take everything after what we're removing. Oh, that's index of. There's remove from index. We have to take everything after where we're removing. That's the loop from I plus 1. And we have to shift it down, right? So let's say I want to remove this 0, right? Well, if I want to remove this 0, I'm going to be sending that to the user, and then I got to go through every one of these, right? This is just like the adding it index, isn't it? I have to remove each one of these things and shift them over. So I think you can see, worst case scenario, I do remove from front. Absolute worst case scenario, this is O in. I have to go through every single data point and shift them over. Best case scenario, I'm removing from an index, and that index is the very end. So, but what's the average? What's the average? Somewhere in between, right? Well, that's n divided by 2. But what did we say about n divided by 2? It's really just n. We don't consider those kind of things when using big O notation. Okay, so I think we have our answer there. That this is O in. This remove from front then is definitely O in. It's always O in. All right. What about index of? Index of was when we went through and we found a specific value and returned the index where it was located. So we started our loop at the beginning. So if I was looking for the number 7 in this list here, backed by the array that I'm showing, if someone says, what is the index of the number 7? Well, I'd say, well, that's easy. It's the first one I check, right? But if they ask for the index of 12, well, then what I would do is I would say, okay, let me start with the first place. It is not here. Move over. It is not there. Move over. It is not there. Move over. It's not there. Finally, I found it, and then I return that index. So I think you'll agree with me that in best case scenario, index of is O1. Worst case scenario, I got to loop and check every single data point. And if there's in items, that's O in. What's the average? You got it, O in. We don't get to say O in over 2. So we're going to say this is O in. At best, O1, but we're just going to give the average runtime of O in. I like using capital N instead of lowercase. All right. What about set? With set, we find a specific place in the array that's backing our list, and we swap it, right? So let's say that I wanted to say, oh, let's set 3. So I got this list, and I say, oh, you know what? I want to call set on index 3, and I want to make it a 4. Okay? Well, we know that that means I have to find a third index. So for me, I have to count 0, 1, 2, 3. But the computer, it doesn't. With an array, we get to directly access any place in the array. So I'm going to return what used to be there to the user, and I'm going to put the 4 there instead. So it takes about 3 steps to think about it, but it's basically O1. And you can see how that works, right? That we don't have any looping, any shifting, any moving. This is O1. So the set, really good. Returning size, it's clearly O1, right? And I'm not going to list the expand. Let's summarize, before we leave this lesson, what we found about array lists. So these array list methods kind of come in 2 different varieties, right? So we have what I would call fast, and I would call slower, okay? They're not super slow, but they're definitely slower. So what was it that our array list was really good at? We're really good at adding to back. So if you are, and we're going to learn lots of data structures, but if you want to be able to add to a list at the back, like you don't really care to put it in the front of the list when you add something, but you just want to put things in on the back, boom, array list is totally for you. Let's think what else is our list backed by an array so good at. Well, we are really good at removing from back. Can y'all hear my parrot? He doesn't like me to talk to other people sometimes, but he wants to join in. Anyway, adding to the back, removing from the back, and getting at an index. What else is this good at? Really good at setting. And there's some things that it was definitely a lot slower at. Adding to front is intolerable, right? Removing from front, and I want to make those specific because we are going to oftentimes want to work from the back of a list, and other times work from the front of a list. And so having access to the front and the back quickly is going to be something that's important to us at times. So adding the front, removing the back, adding an index is definitely slower. We saw that. What else is slower? Removing at an index. And I will also continue this slower. Finding the index of a value. That's slow. It is. Our data structure for a list is not built to be able to find something quicker. How could we make it quicker, right? Well, how about we alphabetize it? I mean, it's just like with computers. Humans are the same way. We can find things quicker when they are organized. We're going to look at lots of different ways to get a faster speed than that. with different data structures. But you're going to see that anytime, these are all ON, anytime we're going to try and move one of these things over here, it's usually going to come with some sort of sacrifice. And there is no best data structure. There's a best data structure for the job that you have. And what we're going to study more and more of these so that you learn how to pick one that works best for you. Okay, in our next lesson, we're going to move into making our list able to hold other things besides integers. We're going to learn a little bit about generics, and then we'll wrap this whole thing up by learning about some of the abstract collections, interfaces, and things like that, so that we can make our list really powerful and really useful when we combine it with the Java collections framework. So look forward to seeing you again next time. For now, that's all.